welcome to all of you in this session on machining. So, in the last lecture we have started the discussion regarding the basic machining operation, like how machining is performed. We have seen that what is the necessity of machining, why do we require to go for a operation like machining when we have already net and near net type of manufacturing technologies or manufacturing processes like casting, forming that are already available with us. So, what is the application spectrum of machining, where machining is required, all that was discussed in the last lecture. So, today we will start our discussion regarding the different other aspects of machining. But before we start our discussion regarding the other aspects of machining operations, we will just like to review what we have discussed in the last lecture, so that a continuity in the lectures is maintained. So, yesterday we discussed the basics of machining operation. The first lecture was titled as machining fundamentals. So, we have discussed that what are the machining fundamentals, why machining is required, how does it compare with the other manufacturing processes like casting, forging or other metalworking operations, where does the application spectrum of machining lie. Then we discussed what is the necessity of machining, in which we discuss a number of points where machining has been shown that it is imperative, it is necessary, and it is, I can go to the extent of saying that it is inevitable for certain products. So, there are certain category of products, if we are not going to machine them, we are not going to utilize the complete capability or the complete functions of those particular products. So, machining thereby becomes imperative, or I can say it becomes inevitable. Then what were the limitations of machinings? We have seen the first important and the most important limitation of machining was that most of the material here, or I can say that if we are cutting, then major part of the material, if we are finishing, then smaller material is waste. So, wastage of material is one of the most devastating, or we can say one of the most economically not, we are not able to justify that the machining operation as compared to the normal or the conventional manufacturing processes. In conventional manufacturing processes there is no loss of material, but here in case of machining always there is a loss of material in the form of chips. Then we discussed what are the different types of chips that are formed. So, different types of chips that were discussed were continuous chips, built up edge chips, then we discussed the serrated and segmental chips, and finally the discontinuous chips. So, we have also seen that under what conditions and for what type of materials these type of chips will be formed. Then we discussed towards the end of the lecture what are the chip breakers, why are the chip breakers required, why do we need to break the chip, what are the problem areas with the continuous chips. So, all those important aspects regarding the fundamentals of machining operation were studied in the last lecture. So, today we carry forward our discussion regarding the fundamentals of machining operation. Now, this is a very basic diagram of a very basic model of a machining operation. Since yesterday we have been talking about the rack phase. So, this diagram has been incorporated in order to explain the different elements of the machining operation. So, we can see here that this is the workpiece which is getting machined. So, we can see this geometrical entity, we can call it thickness. So, thickness here is more as compared to thickness at this section. Why? Because some part of the material has been removed from this surface. So, this line is the machined surface. This yellow colored portion give us that this is the cutting tool. Then a chip has been formed. So, in our previous lecture we have seen what are the different types of chips that form. So, that depends upon the workpiece material. This is the workpiece. So, the material of the workpiece, suppose it is a ductile material. So, the chip that we will get will be a continuous chip, whereas if this workpiece is a brittle material, then there are chances that the chip will be a brittle chip, or we can say the chip will be a discontinuous type of a chip or a powdered form of a chip. This is the shear zone. If we draw a straight line here, we will get the shear angle. this is the cutting tool. So, these are the important elements in the machining operation. So, wherever we perform a machining operation, these 3 or 4 elements will always come into picture. Always there will be a workpiece on which the machining has to be performed, there will be a cutting tool. Now, the cutting tool will depend upon the type of the machining operation that we are performing. If we are performing the operation of drilling, or we are going to make a hole in a particular material or in our workpiece, then the tool that we will use will be a twist drill or any other form of a drill. If we want to plane a surface, then a planing tool will be used. If we want to shape a surface or on a shaper, then we will use a shaping tool. If we are going to machine a surface or we want to end mill a surface, then an end milling type of cutter will be used. So, depending upon the requirement, this tool will vary. I have only discussed regarding the geometry of the tool. Now, there will be there can be an end mill cutter, there can be a twist drill, there can be a single point cutting tool, there can be a multi point cutting tool. Now, depending upon the geometry, depending upon the requirements, we will choose the geometry. Then this tool can be of any material. We will see as a subsequent part of this lecture that what are the different types of tool materials, what are the requirements from the different types of tool materials, like it should have hot hardness, or what type of properties it should have, that will be discussed as a part of this lecture. Then this workpiece properties also influence the machining operation. Moreover, the types of chips we have already discussed. So, here we see this black portion is the tool and this is the chip that is getting formed. So, this is a very simplified model of a machining operation. Now, if we discuss this is what we are going to continue from the last lecture. We were discussing the chip formation in metals. Now, chip formation in non-metallic materials also takes place in the similar fashion only, or in the similar manner only. So, just I will read it out. Chip formation mechanisms for metals, that we have already discussed, that how the chip formation takes place, what are the various elements that influence the chip formation. So, chip formation mechanisms for metals are generally applicable to non-metallic materials also. So, the mechanism of chip formation will remain same in case of non-metallic materials also. A variety of chips are obtained in cutting thermoplastics. Now, thermoplastic is one non-metallic material that has been chosen. Depending upon the type of polymer as well as the process parameters such as depth of cut, tool geometry and cutting speed. Now, one example has been given of thermoplastics. So, if we are cutting thermoplastics, then the basic mechanism of chip removal or the chip formation will be same, but it will depend upon the type of the polymer. The type of the polymer says that here also it will depend upon the type of the workpiece material that we are machining, as was in the case of metals. If it is a ductile material, the chip formation will be different. If it is a brittle material, the chip formation will be different. Similarly, in case of thermoplastics also, if it will depend upon the type of the polymer that has been chosen for machining operation. So, a variety of chips are obtained in cutting thermoplastic depending upon the type of the polymer. So, workpiece material will define what type of chips are going to form, as well as the process parameters. Process parameters, what are the different process parameters, that is depth of cut, or it can be the cutting speed, or it can be the feed rate. So, depending upon the process parameters also, it will dictate that what type of chip formation will take place. Moreover, the tool geometry will also dictate that what type of chip formation is going to take place. For example, yesterday we have seen that rack angle will influence whether it will be a continuous type of chip formation or it will be a discontinuous type of chip formation. So, rack angle, what is rack angle? Rack angle basically defines the geometry of a cutting tool. So, the tool geometry will also define that what type of chip formation will take place, or it will dictate that what type of chip formation should take place while machining a thermoplastic material. Similarly, the cutting speed will also influence, already that we have discussed. Thereby, being brittle, we have discussed the thermoplastics, what are the various factors that will influence the chip formation in a thermoplastic. Similarly, being brittle, thermosetting plastics. So, initially we have considered only the thermoplastics, now we are considering another category of plastics, that is the thermosetting plastics. So, being brittle, thermosetting plastics and ceramics produce discontinuous chips. So, here also the thermosetting plastics are brittle in nature, whereas the thermoplastics has some kind of they will undergo some kind of deformation and some continuous form of chips may be formed. Now, if we take an example of chip formation in non-metallic materials, if we take example of fiber reinforced plastics, whereby these plastics, it can be thermosetting also, it can be thermoplastic also. When these plastics have been reinforced with fibers, the fibers may be of carbon, these fibers may be of graphite, these fibers can be aramid fibers or these fibers can be glass fibers, or depending upon the type of the fiber that has been chosen, as well as the matrix that has been chosen to form a composite material. The chip formation will depend upon the number of parameters that we have already discussed. So, first important parameter is the material out of which it has been formed. If we take a case whereby we considered that it is a thermoplastic. Thermoplastic means the matrix is made up of a plastic which is a thermoplastic and the fibers are suppose glass fibers. When we machine it, then the type of chip formation that will take place will be entirely different if the matrix material is thermosetting plastic instead of a thermoplastic. So, it depends upon the basic ingredients of the raw material or of the product that we are designing or of the component that we are machining, that what type of chip formation will take place, but the basic mechanisms of chip formation will remain same. It will not vary too much as in the metals as well as in the non-metallic materials. Now, we come on to another important aspect of machining, that is the cutting forces and power. We need to study the cutting forces and the power requirement. Why? Because as we have already seen that when the tool is going to cut the workpiece, there will be a number of stresses that will be developed, that they will induce certain forces on the tool as well as on the machine tool. The cutting tool will undergo some forces, or it has to undergo certain forces, as well as the some forces will also be exerted on the machine tool. So, the tool as well as the machine tool, or we can say very simple, in the very simple language, the tool, the cutting tool or the machine, both have to be sturdy, both have to be rigid, so that these forces that are generated because of the cutting action do not cause any form of distortion to the tool or to the machine. So, we need to understand what type of forces will be generated, what will be the direction of these forces, how these forces should be controlled. So, all these parameters have to be studied. Moreover, when we select a particular machine for a particular operation, we have to specify it, and the power is one of the important specifications that has to be provided. If we have to machine a very hard material or a material with a very high strength, then the forces that may be encountered in machining that high strength material may be extremely high. So, when the force requirement is very high, so power requirement may also be high. So, we need to select a machine tool, or we need to select a machine which can sustain, which can provide that kind of power and which can sustain that kind of forces. So, there is an important discussion that is regarding the cutting forces and power that should be done, or important knowledge base should be developed regarding the cutting forces and the power before selecting a particular machine. Now, just to see what we have been discussing for cutting forces and power, the knowledge of the cutting forces and the power requirement is important. Already we have discussed all these things. Power requirement must be known to enable the selection of the machine tool. Already we have discussed that when we are faced with a problem to select a particular machine tool for machining certain materials, we have to have a knowledge of the power requirements. If we are not knowing the power requirement, if we take a machine just without considering the power requirements for that particular machining operation, the machine may not operate properly, or there may be too much of vibration and chatter. So, already we have seen in previous lecture that this vibration and chatter will cause a lot of problems in the proper machining operation, and if the machining operation is not proper, what are the different types of problems that will be encountered. These problems may range from the deterioration of the surface finish to the excessive tool wear or sometimes the tool failure also. So, we need to control these cutting forces, we need to control these we need to avoid the deterioration of the surface finish, and we need to avoid the tool breakage also. So, in order to control all these parameters, we can only say that there should be no vibration and chatter when the machining operation is being done. So, in order to avoid vibration and chatter, we should select a particular machine tool or a specific machine tool which can sustain or which can control the forces that are being generated, so that the machine tool should be such that it should have sufficient rigidity, it should have sufficient stiffness. So, the power requirement must be known to enable the selection of the machine tool. So, the power requirements must be known to enable the selection of a machine tool. Similarly, the cutting forces enable the proper design of the machine tools to avoid excessive distortion of the machine elements. So, we have been discussing the same point from the last slide also, that the cutting forces enable the proper design of the machine tool. If we are not knowing the cutting forces, then the machine tool may not work properly, or the design may not be according to the requirements of that particular machining operation. So, excessive distortion to the machine elements should be avoided. What are the different problems of excessive distortion that we have already discussed in the previous point? So, excessive distortion, vibration, chatter, all these things have to be avoided, and how it will be avoided? If we have a prior knowledge that what are going to be the forces that will be encountered during this machining operation, what are the power requirements for this machining operation. If we are knowing what is going to be the forces and what is going to be the power requirement, we can very easily control different type of problems that may later on result if this consideration is not given at the onset only, or at the beginning. If we are not going to give this consideration regarding the cutting forces and the power requirement, then all these problems of distortion of the machine element or vibration or chatter or deterioration of the surface finish or excessive tool wear or the breakage of the tool may take place after some time. Now, whether the workpiece is capable of withstanding the cutting forces, this also is important point. The workpiece material will define that whether it will be able to sustain that kind of cutting forces or not. We may take a material which is not able to withstand those kind of cutting forces that are generated because of that operation, then the material will fail and will not be able to use it for its intended function. So, knowledge regarding the cutting forces as well as the power is important for the smooth as well as the proper performance or the proper operation of the machine. Now, coming on to measuring the cutting forces. Now, we have been discussing that the cutting forces are important, the power requirement is important, we should have prior knowledge regarding the cutting forces, we should have prior knowledge regarding the power requirement. But how to measure the cutting forces? Now, the cutting forces can be measured using a suitable dynamometers with resistant wire strain gauges or force transducers such as piezoelectric crystals mounted on the machine tool. Now, we can measure the cutting forces, it is not too difficult. We can also estimate or we can also analytically calculate the different elements of the forces, different types of forces that are generated. So, there are theories that have been developed for machining of materials, in which we see that we can analytically estimate or analytically calculate what are the forces that are going to be generated for this operation. So, here as a part of this lecture we are not going to consider the analytical aspect, because this is the general discussion regarding the machining operation. But we can experimentally also measure that what are going to be the forces that are going to be generated while machining this particular or that particular material. So, two important measuring instruments or measuring devices has been given in this point. This is the resistance wire strain gauges or the piezoelectric crystals. These can be used to measure the forces. So, how this is incorporated? If we are going, suppose we take an example of a drilling operation. Now, the drill is given a motion, suppose this is the z direction. So, the drill is given a motion in the z direction and the workpiece is in the xy plane. Now, when the drill is coming and it is going to make a hole inside the workpiece, that is in this plane, then below this workpiece we can mount a dynamometer. So, this dynamometer can work on any of the principles as shown on your screen. There are two principles that have been shown. The first one is the resistance wire strain gauges and the second one is the piezoelectric crystals. So, any of these two can be used and we will mount the dynamometer that we have selected below this workpiece. So, when the drilling operation is taking place, this 4 component drill dynamometer can be connected to the charge amplifier and to the display. Now, this display can be a digital display or the display can go directly into a computer system where we can see that how the forces are varying with the time and how what is going to be the magnitude of the forces. Now, magnitude of the forces that are being generated can be seen on the y axis with the time on the x axis. So, we will be able to see that how the forces are varying, whereas if we have a digital display, we can have a maximum value of the forces that have been generated in this drilling operation. So, it depends that for what purpose we are recording the forces. If we are only recording the forces to know that what is going to be the maximum force for drilling a hole in this particular material, we can have a digital display on which we will know that this is going to be the maximum force, or we can say this is going to be the maximum torque. There will be different types of forces that will be generated during the drilling operation. But if we want to go in for further analysis that how the force is varying when the drill point touches the workpiece, what is the force when it is doing the drilling operation, when the lips are completely in engagement with the workpiece, what are the forces that are generated, what are the forces generated when the drill has come out of the hole or has started to come out of the hole. So, that particular behavior of the force with the time during the drilling operation can be seen on a xy plot and try to understand that how the force is varying with time when a drill is making a hole inside a workpiece. So, using any of these instruments we are able to measure the forces. So, these forces can later on be used for a number of usages. As we have seen, if we know that for this particular material this is going to be the force requirement, this is going to be the power requirement, or these will be the forces that will be generated and this will be the power that will be required, very easily we can select a particular machine tool for the said operation. But if we are not knowing the forces, if we are not knowing the power requirement, then if we do the guesswork, the machine tool that we may buy may not be able to perform the intended function of making a hole or for end milling or for shaping or for whatever purpose we have selected a particular machine tool may not serve the intended function of for which it has been bought or for which it has been selected. Now, coming on to the temperature in cutting. So, we have seen that different types of chips are formed, then there are cutting forces and power requirement, that is important to understand. Then the important point is the temperature in cutting. Now, we have seen that when a tool is in direct contact with the workpiece, the heat is generated and the temperature elevates, or there is an elevated temperature or elevated heat zone that is prevalent between the tool and the workpiece. Suppose this is the workpiece and this is the tool. When the tool is in direct contact with the workpiece, in this zone the heat is going to be more. Now, some part of this heat we have discussed earlier also will be taken away by the chips, then a substantial amount of this heat will go to the workpiece and some amount of heat will also go to the tool, but the maximum amount of heat will be carried away by the chips. But that temperature rise is not only going to affect the chips, because the chips are getting removed anyway, but it is going to have an effect on the tool as well as on the workpiece. So, the energy dissipated in cutting operations is converted into heat. So, when the tool is in direct contact with the workpiece, so the energy that is dissipated is converted into heat, which in turn raises the temperature of the cutting zone. So, the cutting zone is the zone where the tool is in contact with the workpiece. So, the raises the temperature of the cutting zone. The knowledge of the temperature rise is important. Now, this temperature rise that is taking place because of the heat generation in the cutting zone, we need to understand. The knowledge is important for a number of factors that we will be considering now. The knowledge of cutting forces and power requirement is important, that we have already seen. If we are not knowing, then there may be some problems at the later stage when we have bought a machine tool and it is not satisfying the intended function. Similarly, the knowledge regarding the temperature generation or regarding the heat generation during the cutting operation is equally important. So, we need to understand it for the following reasons. The excessive temperature adversely affects the strength. Excessive temperature means the temperature beyond a certain limit adversely affects the strength, hardness and wear resistance of the cutting tool. So, there are 3-4 points that have been addressed here. Excessive temperature adversely affects the strength. So, first important point is the strength will be affected by the increase in the temperature. The hardness will also be affected. Moreover, the wear resistance will also be affected. So, 3 important parameters of the cutting tool are getting affected by the increase in the temperature in the cutting zone: strength, hardness and wear resistance. Now, the cutting tool is an important element of the machining system. If our cutting tool is not performing its function properly, then whatever is the intended function, whatever is the surface finish requirement or whatever is our desired quality, that will not be attainable. So, it is important that the temperature in the cutting zone has to be controlled. For example, here we take only one important aspect, that is hardness. Now, machining we have already discussed, it is a operation where we use or we employ the aspect of relative hardness. There is a workpiece, there is a tool, the tool comes and performs its operation on the workpiece. The tool has to be harder than the workpiece, but because of this operation the heat is getting generated and it is losing, the tool is losing its hardness. If the tool loses its hardness, it is not going to perform the intended operation or the machining operation for which it has been used, and if it is not going to perform the operation, then there are chances that the surface finish that we will get will not be good, or sometimes it may so happen that no machining itself is taking place. So, the temperature control is also very important. Now, excessive heat makes it difficult to control the dimensional accuracy of the part being machined. So, initially we have seen the first point that the heat that is being produced or the temperature that is being raised in the cutting zone is going to affect our cutting tool. Here we see that the excessive heat will also affect the workpiece. So, the excessive heat makes it difficult to control the dimensional accuracy of the part being machined. So, the dimensional accuracy of the part, in the very beginning when we started our discussion regarding the machining operation or the machining fundamentals, we have seen that all these products can also be made. I should not say all, but most of the products that we are machining are made initially by the near net or net shape manufacturing technologies like casting, forging or metalworking operations. but later on, in order to improve the dimensional accuracy of the part, we perform the machining operation. But if there is an elevated temperature or there is a heat generation in the cutting zone, then the dimensional accuracy of the part being machined is suffering or is getting deteriorated. So, the dimensional accuracy that for the purpose for which we are performing the machining operation is getting defeated. So, the important point to note is that we have to control the temperature in the cutting zone. Now, the third important point to understand regarding the heat that is generated in the cutting zone is that increased heat may result in thermal damage to the machined surface, adversely affecting its property. So, increased heat may also result in thermal damage to the machined surface. So, it will affect the properties of the surface that we are generating. So, basically we are performing a machining operation to improve the surface finish as well as the surface integrity of the surface. But if we are raising the heat or we are not raising the heat, in fact the heat is getting raised heat is getting generated because of this particular machining operation. When the tool is in direct contact with the workpiece, the heat is getting generated. So, it is a phenomenon that is inevitable. So, when heat is generated, we have to avoid this heat. Why? Because we have seen that these elevated temperatures are not only going to affect the cutting tool, but these are also going to affect the machined surface, and they are going to impair the surface quality as well as the surface integrity. Moreover, elevated and uneven temperatures may distort the machine tool and result in poor dimensional control of the workpiece. So, till now we have seen the heat is generated, alright, agreed. When the heat is getting generated, it is going to affect the cutting tool, it is going to affect its hardness, it is going to affect its strength. Similarly, the elevated temperatures are going to affect the workpiece also. The dimensional accuracy will be deteriorated or the dimensional accuracy will be affected. Moreover, the surface quality or the surface finish will be affected, the surface integrity will be affected. Although two important elements have been addressed, we discussed in our last lecture that there are three important elements of machining operation or three important elements of machining. What are those three important elements? Those three important elements were the workpiece material, the tool material as well as the machine. So, when the heat is getting generated in the cutting zone, the tool is also getting affected, the workpiece is also getting affected as well as the machine tool is also getting affected. So, when the machine tool is getting affected, it results in poor dimensional control of the workpiece. So, the workpiece is getting affected because of the distortion in the tool, the machine. When the machine is getting affected because of the temperature. This may be a rarest of rare phenomenon, because the cutting zone is far at a large distance from the machine tool. It is maybe a machine tool bed or a machine tool head or a machine tool tail stock. So, the distance is there. The temperature rise will take place only in the cutting zone. So, cutting zone will be at a substantial difference from all other elements of the machine, but sometimes because of uneven heating or because of some high elevated temperatures, this problem may arise. It is not always going to arise, but under certain circumstances, certain special circumstances, these kind of problems may arise, that there is a distortion that is taking place in the machine tool, which is subsequently going to affect the dimensional control of the workpiece. If the machine elements are distorted, the surface finish or the dimensional control of the workpiece that we are machining will not be according to our desired levels or will not be according to the proper quality characteristics or quality specifications for which we are going to perform the machining operation. Now, we have seen that forces are generated, power requirement is there, we can measure the power also, we can measure the cutting forces that are generated also. We have already seen that dynamometers are used to measure the cutting forces. Similarly, the measurement of temperature is also important. Why measurement is important? When we know that what is going to be the temperature that is going to be generated, then only we can exercise some control. We can see that how this temperature has to be lowered or how this temperature generation has to be avoided. If we are not knowing that what is going to be the temperature that is going to be generated during a particular machining operation, it is too difficult for us to exercise the control. So, the measurement of temperature is also equally important. So, we can control the temperature, we will see that we can use cutting fluids can be used as a coolant as well as a lubricant. So, these cutting fluids can control or will control the substantial temperature rise in the cutting zone, but initially we should know that what is going to be the temperature rise in this particular application or this particular machining operation, so that we can properly select a cutting fluid. If we are not knowing that what is going to be the temperature rise, we will not be able to select the specific cutting fluid for that is applicable for that particular temperature rise, and the very purpose of using a cutting fluid will be lost. And if we are going to add another functionality into the machine tool that we are using the cutting fluid also, then no doubt we are also adding to the cost of the product, because the cutting fluid will itself cost something, and moreover the system for bringing the cutting fluid into the cutting zone will be costing something. Moreover, the recycling will also be an important issue that has to be taken care of. So, we are adding another system into our machining operation at some cost. So, the use of the cutting fluid is only useful when we know that what is going to be the temperature rise in our cutting zone or during the machining operation. So, how we can measure this measure this temperature rise, that we will see. Now, temperatures and their distribution in the cutting zone can be measured using thermocouples embedded in the tool and the workpiece. So, we need to understand the increase in the temperature that we have already seen. Now, temperatures and their distribution in the cutting zone. So, in the cutting zone there is going to be an increase in temperature, moreover there will be a distribution of the temperature. It is not that at one particular section or at one particular point, if there is 1000 degrees centigrade, suppose we take example, then at other particular point also the temperature will be 1000 degree only. At one section it will be x, at other section it will be y, at another section it can be z. So, there will be distribution of the temperature. So, the exact measurement as well as the distribution. So, we need to know the magnitude as well as how that magnitude or how that temperature is distributed along the tool and the workpiece, that can be measured using the thermocouples, and these thermocouples can be embedded in the tool and the workpiece. But it is easier said than done. It is a very sophisticated procedure how to embed a thermocouple into a tool as well as into a workpiece. So, it depends that at what particular location we want to measure the temperature, and according to identification of that location we will put the thermocouple there. Then this is not the only technique for measuring the temperature. There are number of other techniques for measuring the temperature in the cutting zone. So, the another technique is the infrared radiation from the cutting zone. There will be a production of infrared radiation. So, the infrared radiation from the cutting zone may also be monitored. So, we can monitor infrared radiation that is getting generated in the cutting zone with radiation pyrometer. So, there is another device or another instrument that we are calling as radiation pyrometer. So, the infrared radiation from the cutting zone may also be monitored using radiation pyrometer. However, this technique indicates only surface temperature. When we are embedding a thermocouple into a tool and a workpiece, we are going to get the temperature at that particular location. Whereas, if we are going to use a radiation pyrometer, we are only going to get the temperatures at the surface of the material or the surface of the workpiece being machined. So, the limitation is that we are only going to get the surface temperatures. if we want to know that what is going to be the temperature in the bulk of the material that is getting machined, that is not possible using this technique. Moreover, the emissivity of the surface, how emissive the surface is, will affect that how sensitive our instrument is and how emissive the surface is. If the emissivity is good, it may so happen that the pyrometer may give us the exact reading of the temperature, but if it is not so emissive, if the emission is less, so it may so happen that we are not able to exactly record the temperature of the surface. So, we can see that it is very easy to record the temperature. If we are using a thermocouple, it is relatively difficult. If we are using a pyrometer, it is relatively easy, but depending upon the application areas, each of this process has its application. Each of this process or each of this instrument or each of this device has its advantages as well as its limitation. So, depending upon the requirement, depending upon the type of the machining operation that we are performing, we can particularly select any one of these techniques. There will be other techniques also for measuring the temperature in the cutting zone, but that because of the time constraints we are not going to go into detail of all the techniques regarding the measuring temperature. We have seen that these are two important techniques with which we can establish that what is going to be the temperature that is going to be generated at the cutting zone. So, once we are able to establish the temperature as well as the distribution of the temperature in the cutting zone, we can then go forward and select that what is the type of cutting fluid, how we should inject the cutting fluid, what should be the application technique of the cutting fluid for controlling the temperature in the cutting zone, what should be the properties of the cutting fluid for controlling this much temperature rise inside the cutting zone. Now, we have seen cutting forces, temperature in the machining operation. Now, we come on to another important aspect which is directly related to the economics of metal cutting. We have to justify a process economically so that it competes with the competitive processes. Now, tool life, why tool life is important? Wherever we go, this is a regular cost that is incurred by any plant that is based on the machining as a important manufacturing process. Once if we acquire a machine tool, that machine tool is a permanent asset, but these tools regularly add to the cost. So, it is a regular cost that is associated with the tools. Moreover, if we are not properly operating or if we are not performing the machining operation properly, this tool life will be adversely affected and we are not going to we will not be able to economically justify the operation. Now, tool life has two important points, that is wear and the failure. So, wear is anyhow going to take place whenever, suppose one particular example that comes to my mind of wear or friction is that when we use a pencil, we write with a lead pencil I am talking about, not with a pen, a lead pencil that is used by children. When a pencil is used to write something or to scribble something on a piece of paper, so the lead wears out. So, that is one advantage of wear, we can say. Although as an engineer, as an scientist, one can say that wear is always detrimental, but sometimes the wear is also useful. For example, the pencil, when we rub a pencil on a piece of paper, a line is created or some words are written. So, there also the lead is wearing out. But here, coming on to our discussion, tool life which incorporates wear and failure, the wear has to be avoided. We want that the tool material or the tool that we have selected should not wear out very fast. If in case it wears out very fast, then we have to replace the tool either, or we have to regrind the tool or redress the tool. Now, regrinding will also add to the cost. So, when we select a particular tool material, we have to make this thing, or we have to bear this thing in our mind, that its wear rate or the wear should be minimum. So, the tool life will depend upon the wear, that how the tool is getting worn with the time. Now, the cutting tools are subjected to, why we are giving so much of importance to this tool life or and wear and failure, because the cutting tools that we are using, they are subjected to high localized stresses. So, we have already seen when the tool is in direct contact with the workpiece, highly localized stresses are developed, and because of which the plastic deformation or the failure takes place, or some of the part of the workpiece is removed or detached from the workpiece in the form of chips and gets removed. So, that highly localized stresses are generated. So, first point is that the tool undergoes highly localized stresses. The second is high temperatures. We have already seen while machining operation, a cutting zone, high temperatures are generated, or it is a zone where the heat is more, or heat is generated in the cutting zone. So, because of that heat, there are elevated temperature, and at elevated temperature the hardness, the strength, as well as the wear resistance of the tool is going to be affected. So, highly localized, it is subjected to highly localized stresses. That cutting tools are subjected to high pressures. Then the sliding of the chip along the rack face. So, in the very first diagram that we have seen today in our lecture, that there is a cutting tool and the chip goes at the face of the tool like this. So, this basically is the rack face of the tool. Suppose this is a tool, this is the rack face of the tool, and the chip goes over the rack face of the tool like this. So, this rubbing action between the chip is a work hardened material sometimes. So, when this hard material is rubbing against the tool rack face, there is always going to be some effect on both of these, but the chip is not going to be used for any other purpose. It is a waste material only, but the tool rack face has to be used again and again. This tool has to be used again and again. So, when the chip is causing a abrading action or wear on this particular rack face, then there is going to be certain failure of the tool after some time. It is not that once the chip has rubbed, the tool is going to break, but gradually when the chip is continuously rubbing against the tool after some hours of service, maybe I say that the tool after 10 hours of service, there may be some kind of wear that will be noted on the face of the tool. So, that has to be avoided. So, the cutting tools are subjected to high stresses. These can be compressive or tensile depending upon the type of application. So, high localized stresses, high temperatures, sliding of the chip along the rack face, and sliding of the tool along the freshly cut surface. Now, when the tool is doing the machining operation like this, the tool also has two faces. Suppose this is the tool that is going like this. So, this face and the machined face, suppose this is the machined face, when this is moving, if we are not providing a proper relief angle or we are not providing the proper tool geometry, one face of the tool may rub against the machined surface, and subsequently we will note some kind of wear on the surface of the tool that is rubbing against the freshly generated machined surface. So, it is important for us to understand all these phenomena which a tool undergo or a cutting tool undergoes in order to ascertain a tool life of the material. If the tool is subjected to highly localized stresses, it is subjected to high temperatures, it is subjected to rubbing action of the chip along the rack face of the tool, or one face of the tool is rubbing against the freshly generated machined surface. So, why all these things are, what all these things are going to result into? All these things are going to result into the tool wear, and that will later on result into the tool failure. So, the tool life will depend on all these parameters that we have just discussed. Now, these conditions include tool wear, which in turn adversely affect the tool life. So, we have already seen this point, I have already addressed in the previous slide or previous transparency. We have seen that there are different conditions that the tool has to undergo. What were those conditions? Those conditions were stresses, temperatures, high temperatures, then rubbing action, abrading action. So, what all these conditions are finally going to lead into? If all these conditions the tool has to undergo, this will result in tool wear. All these parameters that we have just discussed, all these parameters will lead to tool wear, and this will adversely affect the tool life if the wear is more, because if we would have discussed in detail, there are two different types of wear that we will see as a subsequent part of this lecture. So, different types of wear mechanisms are there, different types of wears are recorded. Now, the wear that we see has certain particular critical levels. If the wear takes place beyond a particular level that has been set, then the tool has to be either discarded or has to be reground. So, till now we have seen that there are number of parameters that affect or that induce a tool wear, and tool wear adversely affects the tool life. So, this tool wear has a particular limiting factors, and if this tool wear is recorded beyond this particular level, then the tool life is 0, means that the tool life has to be stopped at that particular time only. It will be said that the tool has already undergone its service life and now either it has to be reground or a new tool has to be bought. So, this is a limiting factor on the life of the tool, and that is the tool wear. So, these conditions that we have already discussed, we will not go again to those conditions, induce tool wear, which in turn adversely affects the tool life. So, tool life gets affected by the tool wear. The quality of the machined surface and its dimensional accuracy, and subsequently the economics of cutting operation. So, we can say that all these conditions that we have already considered, they will affect the tool wear. Tool wear is going to affect tool life. We have seen that the tool life will be reduced if too much of wear has been reported. So, we can say the tool is dead now, it is not going to perform any function further. But it is not that it is only going to affect the tool life. The tool wear is not only going to affect the tool life, it is going to have an effect on a number of other parameters also. So, that induce the tool wear, which in turn adversely affects the tool life. All right, till now we have discussed the quality of the machined surface. So, if the tool wear takes place, now suppose if we take example of a single point cutting tool. A single point cutting tool has an important nomenclature element that we can say as the nose radius. While machining, if we say that the nose radius increases beyond a particular limit or the nose becomes too blunt, then during the machining operation it will be resulting into a very poor surface finish. If the keenness of the cutting edge is lost and the cutting edge becomes blunt, then it is going to affect the surface finish or it is going to affect the machined surface. So, if the tool wear goes beyond a particular level, it is not only going to affect the tool life, it is also going to affect the quality of the machined surface and its dimensional accuracy. So, if the tool wear is taking place because of the conditions that we have discussed earlier, this particular tool wear is going to affect the tool life. It is even going to affect the quality of the machined surface that we are going to generate or that we are going to get, as well as its dimensional accuracy. So, the workpiece or the product that we are going to get after machining with the tool which has been worn out will not be according to our desired quality as well as according to our desired standards. Then all this will result into the economics of cutting operation. So, economy is definitely going to get affected. Why economy is going to get affected? Suppose we have a particular dimension of a workpiece that we want to produce. The tool has been worn out. We are using the same tool to produce that particular dimension. So, using the tool we have produced that dimension, but the surface quality that we have got is not according to the desired specifications. What is going to happen? We can't further do the machining operation because there is a limitation on the size of the product that we are producing. This is a material removal process. If we say no, then now we can use another tool and give another cut, then during the next cut some amount of material will be removed and the dimension that we are going to get will be less as compared to the required dimension that is there in the design. So, if that particular situation arises, that particular workpiece on which the surface finish is not good because of the tool wear, that particular workpiece has to be rejected. So, if number of workpieces are rejected like this, then this is certainly going to have an bearing on the economics of the operation that we are performing. Similarly, if tool wear is reported at a very fast pace or at a very fast rate, the tool wear is very fast, then the tool has to be reground again and again, and then the tool regrinding cost will add to the cost of the product. So, the economy is thereby going to get affected. So, the tool wear is going to result into a number of problem areas, but certainly the tool wear will take place, but it should be in a controlled manner. It should not be beyond a critical limit. Then tool wear is generally a gradual process that I have already told that it is going to take place, but it should be in a controlled manner. Much like the wear of the tip of an ordinary pencil, I have already quoted the example of a pencil. So, it is like a pencil, when we keep on writing some wear is going to take place. Similarly, when we are using a cutting tool, some wear is bound to happen, but it should not go beyond a particular level, otherwise the tool life will be ending there and the tool has to be either reground or it has to be discarded or it has to be replaced. So, with this we come to the end of this session on machining. So, we have discussed today some of the basic fundamentals regarding the machining operation, in which we have seen that what tool wear takes place, there are different types of forces, how we can measure the forces, what is the importance of controlling the temperature in the machining operation. So, subsequently we will try to discuss what are the different types of machining operations, and we will carry forward a discussion that we are leaving now into the next lecture. Thank you.